Now let's see the pole and polar of a circle. So what is a pole and a polar for a circle is the topic we're going to discuss for today. So now imagine I take a circle where I take a point P somewhere in the plane. In this plane, I draw a circle and I take a point P. Now the condition is that P is a point anywhere in the plane except at the center of the circle. So with the exception that P does not lie on center of circle is the important note I make here. So assuming that P does not lie on the center of the circle, now if I take a point P in the plane, then let me draw few chords of contacts. Say I draw some lines cutting the circle and passing through P. This is one circle, this is another circle, this is another line, and this is another line which it passes through. Now, as I see here, there are many points of intersection which each of the lines passing through P, that is L1, L2, L3, L4, etc. makes with the circle. So these lines which cut the circle and passing through P have different points of intersections. Say line L1 makes the points of intersections A1 and B1, and the line which is this L2 has A2 and B2, then A3, B3, B4, etc. Now this is going to have infinite lines which pass through P and cut the circle. Now let's find the locus of these points of intersection, that is when I take the tangent drawn at P and the tangent drawn at B. At A1 and B1, there are two possible tangents which I can draw to the circle. One is T1 and the other is T2. So for the tangents T1 and T2 which are drawn through A1 and B1, we have a point of intersection which let me call as Q. Now different tangents which intersect through the different points of intersection, say for A1 the tangent is T1 and for B1 the tangent is T2, which intersects at Q, and then, or let me say it intersects at P1, and the tangent at A2 which I draw here and the tangent at B2 which I draw here again intersect at another point, say P2. Similarly, a tangent drawn at A3 and a tangent drawn at B3 again intersect at some point, say P3, so on and so forth, where A4 and B4 gives us one more point of intersection through the tangents. So all the points of intersections P1, P2, P3, P4 are set to pass through a straight line, which is very important geometrical property, that the points of intersections of the two tangents as drawn from the chord of contact of the point P outside the plane just pass through only one line. So here is the line where each of the points of contacts of the tangents pass through, and this straight line which has all the points which are the points of intersections of the pairs of tangents is nothing but the line which is called the polar. So this line where all the points of intersections lie is called polar, and this is called, this point where we draw the actual chords of contacts is called the pole. So this is the polar and this is the pole. So polar is the straight line and pole is the point. So this is how we understand the pole and polar of a circle. Let's recap with the definition. If I take any point P in the plane except that which does not lie on the center of circle, then there is infinite number of chords which I can draw to the circle. So I have considered 4 chords, L1, L2, L3 and L4 are the seconds through which I get different chords out here. So line L1 which intersects the circle at A1 and B1, and line L2 which intersects the circle at A2 and B2, and line L3 which intersects the circle at A3 and B3, and finally line L4 which intersects the circle at the points A4 and B4. Now next comes the pair of tangents which I can draw from the points of intersections. Say for example, I take the chord A1, B1, I draw a tangent through A1 and then a tangent through B1. Obviously, these two pairs of tangents cut at some point, say P1. Similarly, I draw a tangent at A2 and then a tangent at B2, which cut again at some point of intersection, which I call as P2. Similarly, the tangent at A3 and at B3 again intersect at some point of intersection called P3. And A4 and B4 also give another point of intersection which cut at some point, say P4. So these points of intersections, when they are joined through a ruler, gives us a straight line. Interestingly, all the points of intersections are collinear, that is, they lie on the same straight line. So each of the points of intersections, when they form a locus, they form a line which is called the polar, and the respective point is called the pole. The line which is obtained through this point is called the pole, and this line is called the polar. This is how we understand the concept of pole and polar for a circle. Now let's see the equation of polar. Now that we have understood what a polar is for a circle and polar of the point P, which is called the pole, let's see the mathematical formula which is involved with finding the polar of a circle. So if I have polar of the point P x1 y1 with respect to the circle S equal to 0, which is x squared plus y squared plus 2gx plus 2fy plus c, the general equation of circle equal to 0, polar of point P x1 y1 with respect to the circle S equal to 0 is given by the formula S1 equal to 0. So this is the equation of the polar, which is a straight line. So when I want to find the polar of any point P x1 y1 which lies in the plane other than on the center of circle, then equation of polar with respect to that point P x1 y1 is S1 equal to 0, is the equation of the polar. Now let's see the polar with respect to position of pole. That is, what if the pole is outside the circle, on the circle, or inside the circle. So the three cases of the position of a point with respect to a circle, which we have already discussed in the past. So with position of the point, that is the pole P x1 y1 lying outside, on, or inside the circle, are the three cases through which we understand the position of polar with respect to the pole outside, on, or inside. So let's start with case 1, case 2, and case 3, through which initially, if I say I have a circle and I have a point P outside the circle, is one case, and then I have a circle and I have P on the circle, and in case 3 I have a point P which is inside the circle. So with three positions, where one case where P is outside, P is on, and P is inside, let's see what would be the respective polar for three cases of the polars, of the poles in three different positions. So for P outside, let me take, as we have already taken in the previous case of understanding the polar, each different points of intersections have put. Let me also take the chord of contact. We know that the chord of contact is obtained by passing two tangents from P to the circle. So this gives us the chord of contact where they intersect at A and B. So if AB is the chord of contact of point P x1 y1, then each of the intersecting points which I draw through P have the tangents which draw on the extended line. So if this chord of contact, when extended, has all the points of intersection of the tangent, say this is A1, B1, which I draw here, and then they intersect at this point. So each of the pair of tangents which are drawn through the points of intersections of the lines passing through P intersect on this line, which is the polar. So for a point P which is outside the circle, the polar of this pole P x1 y1 is nothing but chord of contact. As you can see, this is the chord of contact which, when extended, has all the points of intersections lying on this line. So case 1 gives us that polar of P is chord of contact. Is very important point which we need to make here. So polar is the chord of contact when the point is outside the circle. Now let's use the definition of polar for a point which is on the circle. So to come with case 2, if I have a point P on the circle, then we know that the polar is when I draw different lines passing through P and cutting the circle. Step 1 of understanding the polar is where I draw each of the lines passing through P and cutting the circle. Obviously, one of the common point would be P because it is the point on the circle. Then the rest of the points are A1, A2, A3, A4, and A5, etc. So these lines are passing through only one point where the locus is the point P. So indirectly, if a point P is on the circle, we say the pole itself is the polar. That is, they intersect at one point. That is, when I take a tangent, then if I draw a tangent at P x1 y1, all these points lie on the tangent. That is, they are coinciding with the tangent. So in case of this case where P lies on the circle, then polar of P is nothing but part of tangent, or we can say it coincides with tangent, is how we understand the case 2. P outside, polar is chord of contact. P on the circle is part of tangent, where I see that all points intersect at one common point P, which is a point on the tangent. Of course, P is the point of contact in this case. The one which makes contact with the tangent and the circle is the pole in this case. Next is when P lies inside the circle. So let's see what is exactly the polar, or how the position of polar is when P lies inside the circle. Now let's come to the third case of the point P lying inside the circle. So let's see the position of polar when P lies inside the circle. So as I see here, if P lies inside the circle, then if I take any two lines passing through P and cutting the circle at 2 points, that is A1, B1 is the chord passing through P x1, y1, and A2, B2 is the chord passing through P x1, y1, then we know that a polar is obtained when I take the pair of intersecting tangents. So for this chord of contact, this is the point of intersection P1, and for this chord A2, B2, the pair of tangents intersect at P2, which gives us the locus where each of the points of intersections, this, or any other chord, passes through the line, which is the locus, that is the polar. So clearly I can see that when P lies inside, the polar does not cut the circle. So the third case gives us the conclusion that polar of P, in this case where it lies inside, does not intersect the circle. So this never intersects the circle. So let's recap with the three cases where here P is outside the circle and each of the polar lies on the line, that is, this is the polar, and here polar is the chord of contact, as we can see here. So the polar, nothing but all the points lie on the chord of contact. So polar is the chord of contact if P lies outside the circle, and polar is part of tangent if P lies on the circle, where all the chords intersect at unique point P with other points intersecting on the other circumference of the circle, and that P gives us the locus where it's nothing but a tangent drawn. A tangent gives us the locus P. Therefore, polar of P is part of the tangent drawn at that point P, x1, y1. Similarly, if I have point P inside the circle, I draw two chords and then the pair of tangents which intersect on this line. And interestingly, I see here that this line never intersects circle, which makes me give the conclusion that if P lies inside the circle, then polar of P does not intersect the circle. This is how I understand case 1, case 2 and case 3 of the polar connected with pole, the position of the point in the circle. Now that we have discussed about polar and its existence with respect to three of the cases as we have taken with pole outside, on or inside the circle, now comes the geometrical properties connected with polar. Say for example, I have a circle for which the polar is this. So if this is the polar, for a point P outside the circle, then with this being the polar, I see that if I join the center of the circle and the pole, then clearly the line joining the center to the pole will always be perpendicular to the polar. So we have to understand that CP, where C is the center of circle, is always perpendicular to the polar of P. Whether P is inside or on or outside, the case is that CP is always perpendicular to the polar of P. Is one of the geometrical property which we identify, and therefore slope of CP, which we know is y1 plus f by x1 plus g, implies this being perpendicular to this, the slope of polar of P x1 y1 is minus x1 by g by y1 plus f. So the geometrical property has led to the property that when slope of the line CP, that is from center of circle to the pole, is y1 plus f by x1 plus g, then the slope of polar of P is given by the formula minus of x1 plus g by y1 plus f, because the product of slopes is minus 1 when the two lines are perpendicular, and therefore this slope norm implies this will be negative reciprocal of the given slope. Slope of polar of P is the formula derived out here. Now let's see the limitations of polar, that is what happens when the pole P x1 y1 is on the center of circle, because in the previous case I have taken the condition that accepting that P lies on the center of circle, we can define a polar. So let's take an exclusive session on why the polar does not exist when the pole lies on the circle, on the center of the circle. So for example, I take a circle with center C. or if the pole is the center of circle itself, then going by the definition of polar, initially we draw the chords passing through P. So therefore, if I take the points, that the chord which passes through this, so this is A1, B1, and there is another point which passes through A2, B2, and etc. So in this case, we get the polar when we join the pairs of tangents. That is, if the tangent A1, if I draw a tangent at A1, say T1, and if I draw a tangent at B1, say this is T2, then the polar is obtained by the locus of all the points of intersections of the pairs of tangents. But interestingly here, we say that the two tangents are parallel. So since for P x1, y1 lying on center of circle, I get two tangents which are parallel. So for this lying on center of circle, I get a chord with pair of tangents parallel. That implies they never meet. That is, there is no locus. That implies there exists no locus of points of intersection. I mean, there is no locus of points of intersection. That implies there exists no polar of P x1, y1 which lies on center of circle.